Hello and welcome to this presentation. If you have clicked on this video, you probably want to know what exactly the research field Automotive of the Josef Ressel Center for Dependable System of Systems Engineering is going to research on. And this is exactly the reason why we are here. We, those are my colleagues, Boris Brankovic and Dominik Krakowiak, as well as myself, Katarina Polanetz. Before we dive right into the topic of automotive, I want to give you a brief introduction. Currently, the automotive industry shifts from purely mechanical technologies towards software-intense approaches. However, software components are still interacting with the hardware inside the vehicle. Accordingly, software is now a partial aspect that needs to be considered within the chain of effects. Consequently, interdisciplinary approaches for the development of such systems are needed. Moreover, nowadays, vehicles cannot be considered as simple independent systems anymore. Vehicles start to communicate with other systems they are surrounded by, for example, other vehicles. This would then be called vehicle-to-vehicle, or for short, V2V communication. An umbrella term for such kind of communication with other systems is called vehicle-to-everything, or for short, V2X. This intercommunication causes the development of vehicles to be even more complex than it already is. The classical development approach, also called document-centric approach, is not only time-consuming, but also error-prone when it comes to consistency. Therefore, the classical approach shall be replaced by the so-called model-centric approach, which is very promising when it comes to dealing with high complexity as well as obtaining the system's quality. At this point, I want to hand over to my colleague Dominik, who is now going to tell you about model-based approaches.
Models have proven to be valuable in the development of complex systems. In the automotive sector, however, the difficulty is that different disciplines are involved, and therefore different languages and tools are used. This leads to a high variety of inconsistent tool chains and development processes in the automotive sector. The challenge is to integrate commonly used methods from other disciplines with those of the information technology. The big gap is to integrate these approaches in such a way that a holistic understanding of the complete vehicle, its subsystems, and their connections is achieved. Model-based system engineering approaches are being looked for in the automotive sector that enable this holistic perspective. Model-driven development approaches are often only used for documentation purposes. In addition, these capabilities should also support requirements engineering, system design, analysis, verification, and validation. The primary use of models for documentation purposes in the automotive sector can be explained by the lack of a formalized modeling language. The Software Platform Embedded Systems methodology, short SPES, was developed to solve this problem. SPES was developed by a National Innovation Alliance created by 21 partners from industry and science, with the goal to make the production of embedded software across industry domains professional. It enables cross-domain and model-based development of embedded systems in different domains. A set of generic viewpoints in combination with a development methodology and concept for decomposition of the system are provided by SPES. The current problems are, on the one hand, the integration of SPES in modeling tools is missing, and on the other hand, the generic concept is often difficult to understand for stakeholders. Now my colleague Boris will tell you something about the domain-specific approaches.
Various frameworks exist in the automotive domain which can be used with respect to model-based systems engineering. However, major drawbacks still exist, as those are mostly from theoretical nature and their industrial applicability has yet to be demonstrated. Those frameworks are language and tool independent, but the particular concern is the availability of a suitable architecture description language, especially with respect to aptness in industry. Therefore, an evaluation of different architecture description languages was done in previous research in relation to automotive model-based systems engineering. The studies have shown that the most suitable language for automotive systems engineering is the modeling language SysML with adjustments. Furthermore, the lack of modeling domain-specific properties and system elements demands an adjustment of SysML and thus a modification of meta-models which allow the usage of domain-related elements. But this is rather meant to be difficult, above all in the case of individual adaptation. To address this aspect, previous researchers examined the possibilities to overcome this complexity and proposed lightweight extensions of SysML by means of an inherent profile mechanism. As a result, a domain-specific language was developed and integrated into a holistic modeling framework, providing modeling support in terms of automation functionality. The chosen approach originates from the domain-specific systems engineering concept, which was originally invented for developing smart grid architectures and was successfully transferred to the automotive domain. The mentioned approach proposes a framework consisting of an appropriate domain-specific language, a suitable process model, and modeling tool. As a result, and on basis of the international standard ISO 42010, the Automotive Reference Architecture Model Framework has been specified and implemented as SysML profile, which makes it possible to model entire architectures in the automotive domain by using a domain-specific language. Thus, the architecture can be modeled from different perspectives, each addressing specific stakeholder concerns by using various diagrams. To complete the mentioned domain-specific systems engineering concept, the resulting domain-specific language was embedded in a toolbox enabling object modeling in the proposed framework. This modeling approach is complemented with an ISO 15288 compliant process model, and the resulting artifacts could have been validated so far on basis of a simplified case study.
However, as the present space methodology gains more and more attention in automotive industries, current research investigates a combination of the space methodology and the automotive reference architecture model. For this purpose, the generic space viewpoints have been complemented with domain-specific model kinds, which originate from the automotive reference architecture model, to get the best out of both approaches. The ongoing integration of the automotive reference architecture model and space appears to be promising, although current work only focuses on a limited proof of concept. Thus, an extension of this proof of concept is important to get more meaningful results and a better understanding. For future research, it will be mandatory to supplement this intention by validating real-world case studies and to integrate concepts towards cross-cutting concerns such as dependability. The next topic, automotive in system of systems, is going to present my colleague Katarina Polanetz.
As I have already mentioned in the introduction, different communication scenarios between vehicles and other systems exist. This interconnectivity between vehicles and other systems has a potential of being considered as a system of systems. Now, a system of systems is a system built from a variable number of smaller autonomous systems which are interconnected with one another. And together they satisfy some sort of higher functionality. An example for such an interconnectivity is electric vehicle charging. So the system vehicle is interconnected with the system grid. And this can also be considered as vehicle-to-grid communication. Now, when it comes to understanding system of systems, a very promising approach is co-simulation. What exactly co-simulation is will be explained in detail later on. But with such simulations, the understanding of the overall behavior of different components can be eased. And research in this field does already exist, however, it still needs to be deepened. At this point, I want to hand back over to my colleague Dominic, who is now going to tell you something about our first main research aspect.
Currently, there are two tools you can use the toolbox with: Enterprise Architect and Rhapsody. But each of these tools has its own implementation of the SPES toolbox. So the goals for the future are that one implementation of the toolbox can support more than one tool, and to connect it with tools from other disciplines, like the control theory with MATLAB or Simulink, and the design modeling with AutoSAR. The overall goal is to make the toolbox independent and to make it a generic, domain-specific language. Now, Boris will tell you something about cross-domain modeling concepts.
Since the domains automotive, energy, and industry 4.0 are growing together within a so-called smart city, it will be important to create a common ground between the considered domains, to enable cross-domain modeling and to foster interoperability. Thus, the research focus will rely on the investigation of meta-modeling concepts like customization of meta-models. One example herefore is the development of generic domain-specific languages that can be used in a multi-domain environment. Further, to overcome the growing complexity within a system of systems architecture, it will be necessary to create a process model aligned with the international standard ISO 15288 to enable development of system of systems in a standardized, uniform way. In combination with generic modeling concepts, a significant contribution of the Josef Ressel Center will be to examine how to describe functions, together with all relevant input as well as output values, disturbances, and interferences. Especially with the introduction of the next major SysML version, new possibilities for modeling functions will be included. Function development in the automotive area is therefore seen as main objective of our work in the center.
The development of more safe and reliable systems covers one main research aspect which addresses the possibility to enable an automated verification and validation process within system of systems architectures. Concepts like formalizing meta-models, for example with graph-theoretic approaches, will serve as basis for our work. Furthermore, the elaboration of suitable case studies with respect to cross-domain architectures and thus concerning system of systems can help to determine crucial components affecting more than one domain. With cross-domain co-simulation, it will be possible to provide an overview of how components behave in certain situations and to make changes in the model prior to development of the component itself. This intention will be part of our research and realize as testing environment for verification and validation of system models. Now I hand over to my colleague Katerina Polanets, who is going to explain you more about the principle of simulations in system of systems.
As it has already been mentioned several times during this presentation, systems become more and more complex. So the understanding of the overall behavior of different components can now be eased with the help of simulations in general. The idea behind co-simulation specifically is that simple systems can be modeled separately without considering the interrelation with other simple systems. After those autonomous systems have been modeled individually, their interrelation can then be simulated using co-simulation. Therefore, co-simulation is a very important aspect when it comes to understanding and developing system of systems. Now, approaches for co-simulation have already been made in the smart grid domain, and the goal now is to transfer such approaches to the domain of space as well. The whole process would now look like this. Coming from the space toolbox, code must be generated from the models within the space toolbox. This resulting source code will then be handed over to a co-simulation framework. After this process has been realized in the domain of space, the next step would then go towards cross-domain simulation. So co-simulation could act as a connection between the automotive and smart grid domain, for example, connecting the space toolbox with the ESCAM toolbox. So space-sided, the vehicle can be modeled, and ESCAM-sided, the grid can be modeled, including, for example, an e-car charging algorithm that takes the electricity price into consideration. Both models now could be developed individually, then transformed to code, and finally handed over to the co-simulation. Such connections would allow to simulate and visualize a phenomenon like emergent behavior. So imagine, during the night, most likely a plethora of e-cars will be connected to the grid, already resulting in higher electricity demand during the nighttime. The more demand, the higher the price gets. If the electricity price rises over a certain threshold, all connected cars simultaneously disconnect from the grid as the price becomes too high to charge. The result is then an abrupt drop in electricity demand. The grid must therefore take countermeasures, and the electricity price falls due to the decreased demand. As soon as the price reaches a level below the threshold, all connected cars simultaneously start charging again, causing the demand to rise again significantly. This process would cause the grid to build up and oscillate, which is called emergent behavior. This problem is one example problem that could be analyzed with co-simulation, and our goal is to find exactly this connection between automotive and smart grid to visualize such problems. This presentation's intention was to clarify the goal of the automotive research field. My colleagues and I hope that you have enjoyed this presentation. And all there's left to say now is thank you very much for your attention and your interest on behalf of the whole Josef Ressel Center team. Thank you and have a nice day.